guys, welcome to Kim Shore. Today we are discussing second year's topic, that is Hess's law of constant heat summation. What is Hess's law? Hess's law is applicable in finding the delta H, that is enthalpy of a chemical reaction. This is applicable in finding the delta H, that is enthalpy of a chemical reaction. Okay. Suppose if the chemical reaction takes place in several steps. Okay. If the chemical reaction takes place in several steps, the enthalpy change of overall reaction is the sum of the enthalpy change of individual reaction. Is the sum of the enthalpy change of individual reaction. Suppose if a chemical reaction takes place in several steps, the enthalpy change of overall reaction is the sum of the enthalpy change of individual reaction. Okay, let's take one example. Suppose a reaction takes place through several steps. We are finding the delta H. We want to find the delta H. The data we know about this reaction is only that the reaction is taking place through several steps. Okay, that is step 1. The delta H is equal to x kilojoule per mole. And step 2, delta H of that step 2 is y kilojoule per mole. And the final step, step 3, the delta H of that individual reaction, step 3, is z kilojoule per mole. And we are finding the overall enthalpy change of this reaction. And we only know about the fact or data about this reaction is that this reaction is taking place in several steps. And we are knowing the enthalpy change of each step. That is step 1 x, step 2 y, step 3 z. Okay, then the delta H of this overall reaction is what? That is x plus y plus z. Okay, x plus y plus z kilojoule per mole. That is the enthalpy change of this overall reaction, chemical reaction. Okay, hope you all got it. Let's take another example. If delta HR is the enthalpy change for the reaction A to D, that is A is the reactants and D is the product. Okay, this reaction takes place through several steps and having different route. That is, if delta HR is the enthalpy change for this reaction, and this reaction takes place in a several steps and the route is somewhat indirect. Okay, that is, suppose if A to D and that intermediate steps are B, C and then D. That is, this reaction takes place through several steps. That is step 1, step 2 and step 3 through different pathway. Okay. The delta HR is the enthalpy change for the reaction in the direct route. That is direct route. The overall enthalpy change for the reaction. And if delta HR 1 is the enthalpy change for this reaction, that is intermediate step. Delta HR 2 is the enthalpy change for second reaction, and the enthalpy change for third reaction is delta HR 3. Okay. Then the delta HR, that is enthalpy change for the overall reaction from A to D. The reaction, the delta HR is the enthalpy change for this reaction, that is from A to D. Delta HR is equal to what? That is delta HR 1 plus delta HR 2 plus delta HR 3. That is irrespective of the path. That is the important point. Since enthalpy is a state function. As we all know that we had already studied, discussed in the in my earlier videos. I had already discussed with you that about state function and path function. That is, since this enthalpy is a state function, it is only depending upon the final and initial states, not on the path. Okay, that is, this enthalpy only depends on the final and initial state. It is not depending upon the path that connect between them. Okay, the path that connect, it does not depend upon the path that connect between them. Okay, this means that the total energy absorbed or evolved in a reaction, the total energy absorbed or evolved in this reaction will be same irrespective of the number of steps. Okay, irrespective of the number of steps, the total energy absorbed or evolved in this reaction is the same. Hence, we can say that this law is somewhat in connection with first law of thermodynamics. That is, the total energy, the energy can neither be created nor be destroyed. The law is thus a direct consequences of the first law of thermodynamics. This is a consequence of the fact that the energy can neither be created nor be destroyed. Here in this, the total energy absorbed or evolved in a chemical reaction, in this reaction, would be same irrespective of the number of steps involved in it. Okay, guys, I hope you all got the basics of this Hess's law. And next we are defining the statement for this Hess's law. Okay, that is, Hess's law states that the total enthalpy change in a chemical reaction is the same irrespective of whether the reaction takes place in one step or several steps under the same condition. Okay, that is, this law, according to this law, you can say that the enthalpy change in a particular reaction is always a constant and is independent of the path. Okay, independent of the path or manner by which the reaction takes place, whether it is 3-step or 4-step or 5-step, the overall enthalpy change is a constant. It is irrespective of the path. Okay. Hess's law states that the total enthalpy change in a chemical reaction is the same. Irrespective of whether the reaction takes place in one step or several steps. Several steps under the same condition. This is the statement for the Hess's law of constant heat summation. Okay, the total enthalpy change in a chemical reaction is the same irrespective of whether the reaction takes place in one step or several steps under the same condition. Now next we are discussing the applications of Hess's law. Application, that is most of the enthalpy change are calculated or determined by experimentally. That is, by experimentally we are determining the enthalpy change of a reaction. But there are some chemical reaction. There are some chemical reaction which cannot be experimentally determined. Okay, there are some chemical reaction which cannot be experimentally determined. It is very difficult to measure or calculate the value of enthalpy change determination through experimentally. It is very difficult to find out the enthalpy change for some of the reactions through experimentally. So what will you do? We can use this Hess's law of constant heat summation for calculating the value of overall value of delta H. Okay. Let us take one example. It is the formation of carbon dioxide. Okay, this is the one step of formation of carbon dioxide. It is carbon plus oxygen, which is in gaseous state, carbon dioxide, gas. This is also in gas, but carbon is in solid state, that is form of graphite. Okay, graphite. Now let us consider the multi-step, that is intermediate step of this formation of carbon dioxide. Okay, that is this reaction takes place in two steps. This reaction takes place in two steps. This first step is the carbon dioxide, this graphite in solid state, plus half oxygen, which is in gaseous state, giving carbon monoxide. Carbon monoxide, which is also in gaseous state. The enthalpy change for this reaction, that is delta HR, equal to what? It is negative 110.5 kilojoule. Okay, now the second step is carbon monoxide gas plus half O2, that is oxygen gas giving carbon dioxide. And the overall, by adding this, we are getting carbon plus oxygen. This monoxide gas cancel out, and R42 plus R42, 1O2. Okay. Carbon dioxide gas, okay, which is in graphite form, and solid state, which is in gas, which is in gaseous state. And the enthalpy change for the second step is minus 283 kilojoule. Okay, now next, what is the overall enthalpy change for this reaction, that is formation of carbon dioxide, is the, by adding these two, okay, this total standard enthalpy change. Total standard enthalpy change in this two-step process is delta 110 negative, this plus, by adding these two, it is equal to negative 393.5 kilojoule. That is the overall, this negative 393.5 kilojoule is the overall enthalpy change for this reaction. That is, here we are added this chemical equation. That is second application of Hess's law. That is, the chemical equations can be added, subtracted and multiplied or divided with suitable numbers, just like algebraic equations. That is the second application of Hess's law. That is, first application is what? We can find out the heat changes, enthalpy changes of various reactions which cannot be experimentally determined. Okay, we can calculate the enthalpy change for those reactions which cannot be experimentally determined. And the second application of Hess's law is that is, it emerges from the Hess's law. What? The chemical reaction, this type of thermochemical reactions can be added, subtracted, multiplied or divided with suitable numbers, just like algebraic equations. Okay. Let us discuss with one example. This first one, determination of enthalpies of allotropic transitions. Allotropic transition means the carbon in one form, one allotrop, that is carbon in one allotrop means in diamond is converted into carbon in graphite form. Okay. Delta H transition for carbon in diamond form is converted into carbon in graphite form. Is the enthalpy of this reaction, which cannot be directly determined, and we can calculate this enthalpy of transition of this transition, that is allotropic transition, from by using Hess's law. Okay, so let us write C graphite, which is in solid state, plus O2 gaseous, C plus O2, CO2, which is a carbon dioxide gas. The enthalpy of this reaction, that is combustion of carbon, that is enthalpy of combustion of graphite, negative 333.5 kilojoule per mole. You can write this equation as equation number 1. Okay, and the second, C, that is in diamond form. Which is also in solid state, plus O2 in gaseous state. We are getting carbon dioxide. That is here also the combustion, that is burning in presence of air, is known as combustion. That is the enthalpy change for this reaction is negative 395.4 kilojoule per mole. Can write this equation number 2. Okay, and what is the actual delta H transition for this reaction? How can we find? Can you tell me? Can you guess? That is, we had already discussed that the chemical reactions can be added, subtracted, multiplied or divided with suitable numbers, just like algebraic equations. Now next, what we are doing is, this equation number 2 minus 1 gives the delta H transition value for this transition, allotropic transition, that is 2 minus 1. 2 minus 1 gives delta HR, delta transition negative 1.9 kilojoule per mole, that is 395.4 minus of minus, that is plus 393.5. Okay, this is the delta H transition is equal to minus 1.9 kilojoule per mole is the enthalpy change for this transition. That is delta HR transition for this allotropic transition is negative 1.9 kilojoule per mole, which is calculated by Hess's law. Okay. Now next, can take one more example. That is, here we are calculating the enthalpy of formation. Okay, that is enthalpy of formation for the carbon monoxide. Determination. Determination of enthalpy of formation. That is enthalpy of formation of carbon monoxide, which cannot be directly measured. Okay, we can calculate with the help of Hess's law. It is here carbon in graphite form plus O2 gaseous state. We are getting carbon dioxide gas. The enthalpy change for this reaction is negative 393.5 kilojoule per mole. Can write this equation number as 1. Carbon monoxide plus half O2 gas getting carbon dioxide, the enthalpy change for this reaction is negative 283 kilojoule per mole. You can write this equation as equation number 2, and your overall equation is 1 minus 2. It is equation 1 minus 2. Carbon in graphite plus half O2. We're getting carbon monoxide. Okay. And the enthalpy of formation of this reaction, overall reaction is negative that is determination of enthalpy of formation of carbon monoxide. That is carbon plus half O2 gives carbon monoxide, can be determined using the Hess's law by subtracting this equation 2 from 1. Okay. That is just like algebraic equations, we can divide, we can multiply, or we can subtract or add it. Okay. Okay, these are the applications of Hess's law, and we can find out the enthalpy change, and the thermochemical equations can be added, subtracted and multiplied or divided just like algebraic equations. And the statement for the Hess's law is the total enthalpy change in a chemical reaction is the same irrespective of whether the reaction takes place in one step or several steps under the same condition. Or we can define like this also, that is, if a chemical reaction takes place in several steps, the enthalpy change of overall reaction is the sum of the enthalpy change of individual reaction. Basically, if somebody asks you what is Hess's law, you can say that if a chemical reaction takes place in several steps, the enthalpy change of overall reaction is the sum of enthalpy change of individual reaction. Okay. Okay guys, this is all about Hess's law of constant heat of summation. That is application, statement, and it is irrespective of the path, and finally the application of Hess's law. Okay. If you have any doubts regarding this section or anything else, you can post or comment. Okay. Thank you.